Hey, welcome back to another IB chemistry video. Basically, we're just going to continue on answering some of these questions, right? We finished Unit 5. We finished all of Unit 5. So finished all Unit 5. And then now, of course, when you're finished the unit, you need practice. You need exposure to question types. Um, and why that is, and this is something that's tricked me a few times throughout my life. It's just you learn the unit, and you think, okay, I know everything. I know everything. Right? You've seen the worked examples. You've read the material. But you haven't done the questions yourself. So by doing these questions yourself, you teach yourself almost as good as learning the material. By learning how to solve the questions, you learn how to uh, rationalize your way through the answers. So let's work through a few more of these. So we finished number 1 through 5 from your textbook in the last video. But then today, what we're going to do is we're going to try to do 5 to something, depending on how long. I don't want to make this video too long. I'm going to try to make about 15-minute videos. So okay, so let's do number 6 then. So the first part of number 6, 6A, is to define the standard enthalpy. So remember, standard is that symbol in the top right. Enthalpy is H. Uh, Enthalpy change of formation. And then it gives you the symbol. It gives you delta H of formation. So the standard enthalpy change of formation, right? What this was, and you can pause the video right now if you want to try to answer it yourself, or look it up. You're welcome to open your book and review it, and then use that review in order to answer the question. So what the standard enthalpy change of formation is, it's the enthalpy change when, and right, so standard was in a standard state. So we were talking about moles because moles are our S unit. So when 1 mole of a compound is formed, and then this was the standard enthalpy change of formation. So remember, we took all of our reactants in their standard states. So if we were to make like CH4, what the standard enthalpy of formation would do is it would just say, okay, we've got carbon, and we're reacting it with 2 hydrogen in order to form methane. And we were going to calculate this standard enthalpy of formation, because any element in its standard state is 0, so it needs to be in its standard state. So we know hydrogen exists as a gas, and it's found naturally as hydrogen gas, and carbon exists as a solid, and that's how it's found in nature. So that's what we meant by their standard state. So formed from its elements in their standard states oh, and under standard conditions. So So what standard conditions means was that it was done at 25 degrees Celsius and 1 atmosphere of pressure. 1 atmosphere of pressure. So standard conditions, typical pressure, average room temperature, and 1 mole. So that's what we see when we say standard. So the standard is just what we'd find typically in nature. So standard enthalpy for enthalpy is 1 mole of a compound. So something is formed from its elements in their standard states. That's what we said with this one. Their standard states, carbon and hydrogen purely. We can do the same thing for ammonia, NH3, N2 plus H2. This would be a standard enthalpy of formation. Delta H of F is how much energy is required to get from nitrogen and hydrogen to ammonia under these conditions. So what would the enthalpy change be? So we just double this up so we can balance it, triple this, and we're all good. So okay, so let's go to 6b. That's the definition that they needed. So now we've got 6b. So the question, it gives you a table. So it gives you a table. Just give me a second to draw it out. I'll be quiet for a second while I draw this out. Table. Here's the compound. Here's the delta H of formation. We've got C4H8 gas. You've got CO2 gas. You've got H2O as a gas. And this is +1, -394, and -42. And the formula that they give us that we need to work with. So C4H8 plus 6O2 gas reacts to form 4CO2 plus 4H2O. Okay. Okay, so let's talk about what it wants. So basically it says, use this information to calculate the enthalpy change for the complete combustion. So now we need to calculate delta H of reaction. So to calculate the delta H of reaction, this is like what we did yesterday. Delta H of reaction, using delta H of formation. And how to do that is that our delta H naught of reaction is equal to the sum of delta H of formation of your products minus the sum of the delta H of formation of reactants. So if we were to do this equation, we just need to see, where are our products and where are our reactants. And we also have to keep into, right, this value right here is given to us. I should write that down right here. It's given us in kilojoules per mole. So right, delta H of formation is kilojoules per mole, or kilojoules mole. So we have to see, right, we've got 1 mole here, 6 moles here, 4 moles here, and 4 moles here. So let's do this one first. Let's do this one first. The sum of the delta H of formation of products. And then let's do this one second. I'm just going to make a little bit more space right there. Delta H of formation of reactants. So actually it'll be easier to do reactants first, because reactants, right, we've got gas in its standard state. So in its standard state, it's zero enthalpy of formation. So right, gas, it's in its elemental state. We've got 1 mole of this, so our delta H of reactants is plus 1 kilojoules. And now our delta H of formation of products, we've got 4 CO2, so it's 4 times negative 394. And we're going to add that to 4 times negative 42. So that's going to come out to be, or let's do this right here. 4 times, where's the negative side on here? Negative 394 4 times 394 plus 4 times 42. Oh, this calculator does not work that well. I will get my other calculator. All right, I'm back. Okay, so I'll do this calculation off the screen just because I don't like that on-screen calculator. 4 times negative 394 plus 4 times negative 42. And our answer comes out to be negative 1,744 kilojoules. And this is plus 1, so if we were to minus plus 1, so our delta H of reaction is equal to negative 1745 kilojoules. And that'll be our final answer. I hope I did that calculation correct. Ooh. Products minus delta H. I'm just going to make sure this is all right for 16, 16. So, okay. So let's continue going a little bit then. And what we're going to have is, let's work on to number 6.2. Number 6II. So you've got 6A, 6B. So now it says deduce whether reactants or products are more stable. So deduce whether the reactants or the products are more stable. So now we just need to look at, okay, let's look at the energy required to form them. So one doesn't require much energy to form, and the other one requires a lot of energy to form. So and we see that this reaction is highly exothermic. So the reaction is exothermic, which means that it releases lots of energy. So it releases a lot of energy. So in this case, we can see that there's more energy stored in the products than there are stored in the reactants. So bond energy, the energy. Okay, I'll try to write this out in a little bit of a better way. So in this case, our products are more stable than our reactants. And to me, I'd see that based on the reaction being exothermic. So if it's exothermic, it releases excess energy. Uh, it forms more stable bonds and releases the excess energy. The products are more stable than our reactants, and this is the bonds are stronger because the bonds are stronger and more stable than the reactants. And basically that's all we need. So it's just the reaction is exothermic, energy is released. So the products after the reactant, right? If we look at our old exothermic reaction graph, right? We had higher energy molecules. They underwent the reaction, and they, exothermic produces more stable products. Okay, and let's finish the last one. So 6.3. 6III. Okay, so this one says predict giving reason. So predict. Predict the enthalpy change of but2-ene would compare to that of but1-ene. So compare to but1-ene based on bond enthalpies. Based only on bond enthalpies. So this, this question I would like so much because we're only in Unit 5. We're not in an organic chemistry unit, so it's assuming you've done organic chemistry already. So I'll draw out these products for you, or these two for you. So but1-ene and but2-ene. I'll just draw two butane molecules to start. But1-ene is here, and but2-ene is here, and then we fill these in. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. 1, 2. 1, 2, 1, 2, 3. And these are all hydrogens. Okay, so it says using bond enthalpies. So let's look at the formula for them. 1, 2, 3, 4, 6. C4, H, 1, 2, 3, 4, 5, 6, 7, 8. C4, H8, which is the typical formula for an alkene, right? CN, H2N. And this one will be the exact same. Will be C4, H8. And if we look at all of the bonds, right? If we look at all of the bonds, we've got carbon-hydrogen bond, carbon-hydrogen bond, carbon. Got the same amount. So same amount of carbon-hydrogen bonds, and we've got the same amount of double bonds. So in this case, if we were just looking at the average bond enthalpies, right? Average just takes into account, doesn't take into account the difference between these two. Average just says, if we take any molecule, we can take a very, very long molecule, and it says this double bond is probably, similar to this one, and it's probably similar to this one. So, right, but we know that as molecules change, if we got a chlorine group on the end there, it's electron withdrawing. So we're going to weaken that bond a little bit. So basically, we're just comparing the average. So if we were to compare the average of these molecules, is that they would have the same delta H of combustion because the same bonds are present, because all the same bonds are present. All of the same bonds are present. And that'll be the end of question 6. So I'll make another video. I just don't want this one to get too long. So I'll make another one next.